So we can start now.
I'll just check if it's working.
Yes, you can start.
Okay. Good evening, everyone. Welcome to the day 2 of the talk on Introduction to Dynamical Systems with Professor Nikita Agarwal. Before we start the talk, there's an announcement. We will be sharing a link in the chat about the WhatsApp group for upcoming events of Kareli. Feel free to join the WhatsApp group for further updates. Over to you, Harinder.
Yeah. Yes. Good evening, all. So I want to announce that, about the doubts. Like, if you have any questions, then put for the Zoom participants, you can raise your hand, or you can put that questions on the chat box. We will address your doubts in the end. Okay. For the YouTube participant, you can post your doubts in live chat. We will address it in the last. So before starting the session, I want to say, like, if you have any doubts from the previous session, you can ask now. And I think we can wait for 2 minutes or 1 minute. Like, if anyone have doubts, then we can take that. Otherwise, we will proceed with the lecture. Over to you now.
So maybe I can begin, if that's all right with you.
Yes, ma'am, of course.
Okay. So there were a couple of questions last time. One was about proving that orbit of every point on the circle under a rotation where the rotation is an irrational, is dense. And I think I gave a head start to that problem, which is that you just focus on the orbit of 0. Okay. So if time permits, I will discuss the proof today. But that is only if time permits, because I want to cover some other interesting aspects. Second was about reference books, and that I will share at the end of this session. A couple of good reference books which are intended for beginners. And the third question was about relationship between Baker's transformation and the doubling map that I talked about. So let me share my screen, my writing pad with you, and I have this slide where I explain what it is. So, okay, I hope my screen is visible to you.
Yes, ma'am, it's visible.
Okay, good. So, so let me explain what Baker's transformation is. It is different from all the other examples that we spoke about yesterday, in the sense that all the discrete maps that we talked about yesterday were on the interval or on the circle, right? So now I'm going to talk about a map which is on the unit square in R2. Okay? So the space, the state space for me is this interval, cross interval, which holds a unit square in R2. And you define the self map T on this square as follows. It depends on the value of x, first of all. So if x is between 0 and half, 0 included, then the point x comma y in the square goes to 2x comma y by 2. And if x is between half and 1, then it goes to 2x minus 1 comma y plus 1 by 2. So let me explain to you how this map acts. on the square. Okay. So first of all, this name baker is coming from the literal term baker. Okay. So imagine that this square shape is shape of your dough that you have. Now imagine you punch it from the top so that the height becomes half. Okay. So that means if the height has become half, you have same volume of dough, the length would become double, right? And then what you do is, this piece that has gone to the right, you bring it on the top. That is what is happening with this map. So if you start with the square and you partition it into two pieces, left and right, equal pieces, this piece L gets compressed by half, and therefore it gets elongated by twice. So there's a twice scaling in the x direction, and there is a half scaling in the y direction, and that is precisely this, right? Okay. And what happens to the right hand side r? R corresponds to x values from half to 1. So what happens to this side is that it gets again compressed, but then it moves to the top, right? So there is a scaling of factor 2 in the x direction, but then there is a translation by half in the y direction, and which is precisely this. Okay, so that's what is happening. So imagine you apply T to this one more time. What is going to happen? Same thing, right? Now, to understand what happens next, you have to repeat the process. So you imagine you compress like this, it becomes twice in this direction. Whatever is out, you bring it on the top. What happens now is this L and R that is there, one on top of other, comes here. But because you have squished it like that, there is an extra piece that has to go on the top. So when you apply one more time, this is how things are happening. So this is very much like when you knead a dough, you see all these layers coming up, right? That is why the name baker's transformation. Okay, so a baker is basically transforming a dough, right? So this map has, so you can imagine that if you apply T again and again, you'll get more and more horizontal strips alternating between L and R. Now the question was that how is it related to doubling map? So in terms of dynamics, they are kind of different because that map was in one dimension, this is on 2 dimensions. So there is more here in some sense. So this map is an invertible map. And yesterday I said that when you have doubling map and the shift map on sequences, they are related, and we will exhibit that relationship today. But here also, this Baker's transformation has a relationship with a shift map on not sequences which were one-sided like yesterday, but two-sided sequences. So this dot refers to having this. So this dot refers to the starting point. Then you have 0th position, first position, second position, and so on, and also backwards. You take the shift map on this by again shifting by one position. These entries are coming from this set having 2 entries, 0 and 1. And this map, instead of looking at it in this form, you can study the shift map on the sequence space to understand the properties of the original. Okay, so I'm not going to get into this because you need to do a lot of bookkeeping. It's going to take a lot of time. But if you are interested in this, you can pick up any book on dynamical systems, and this is an example that is featured. But the question is, how does it relate to the doubling map? So if you focus on just the x coordinate of this map, right? What is happening to the x coordinate, regardless of the y coordinate? It is precisely the doubling map, right, in the x coordinate. So this map is actually known as a generalization of doubling map in 2 dimensions. Okay, so the doubling, the connection with doubling is basically this part of it, right? Okay, so from dynamics point of view, it's a very important map. It has all the nice kind of features that one wants to study in dynamics. So I'll stop here on Baker's transformation on the question. So I think I've given enough input on this one. So now let me go to the let us begin today's lecture. Okay. So let me start by discussing what we covered last time. So we discussed an informal definition of a dynamical system. So it's a triple having a state space, phase space, and a rule or a law which governs the motion. We looked at several examples of continuous dynamical systems as well as discrete dynamical systems. We tried to understand the idea of qualitative study of ODEs as opposed to finding precise solution to the ODE. And we also discussed, at least stated, the Hartmann-Grogman theorem, right? And the key idea in dynamical systems theory is to study long-term behavior of orbits of points in the state space. So this picture is kind of what we are doing. This is in the discrete setting. You have a state space X. You start with a point X. You apply T, you see where this point goes, which is Tx, then T square X, T cube X, T4X, and so on. So the idea is to see how this orbit is behaving. Or rather, looking at one single orbit, you look at the ensemble of orbits. So you see how on the average orbits behave. Okay. So we'll come to this notion in this talk, but rather than looking at individual orbits, you look at it in a probabilistic sense. Okay. So we'll come to that, as I said, in this lecture. So let me remind you of Hartmann-Grogman theorem from last time, because this is going to be the starting point for today's lecture, and then we will move to discrete dynamical systems. So let me recall what Hartmann-Grogman theorem states. It says that if you have an open subset of Rn containing the origin, and you have a function which is continuously differentiable, which is 0 at 0, let phi t be the flow or solution of this system, and let A be the Jacobian of f at 0, and you assume that A is hyperbolic, which means that it has no eigenvalue which has 0 real part. Then there exists a homeomorphism H from U to V, where U and V are open sets containing 0, such that for each x0 in U, there is an open interval I x0 in R containing 0, such that for all t in I x0 in this interval, there is a relationship between the dynamics of the nonlinear map, nonlinear system, with the dynamics of the linearized system at 0. So locally, one looks like to about 0. So from dynamics point of view. Okay. So let me explain this theorem with an example. So you consider the system x dot equal to minus x, y dot equal to x square plus y. Okay. So xy is in R2, right? So what is f here? F of x comma y is negative x, x square plus y. It's a map from R2 to R2. And f of 0, 0 is 0, 0, right? What is the Jacobian? Jacobian is given by, you look at the first component, you differentiate it with respect to x and differentiate with respect to y. You look at the second row, which is for derivatives of the second component, which gives you 2x and 1, right? So if you evaluate df at 0, 0, it comes out to be minus 1, 0, 0, 1, right? So this is hyperbolic because its eigenvalues are negative 1 and 1, which are both with real part non-zero, right? So let us look at the linear system. Okay, so just the linearized system. What is the linearized system? It's x dot y dot is equal to axy, which is nothing but negative x, y, right? So this is the simplest possible system because there is no interconnection between x and y except for their connection through t, right? So again, I am not interested in the precise solution, even though you can find a precise solution here. So let us draw what happens to points. So let's say this is x direction, this is y direction. 0, 0 is a fixed point, meaning nothing happens. If you start at this point, you stay there. It's an equilibrium. If you start with any point on the x-axis, you look at the sign of the derivative of x. If x is positive, then x dot is negative. That means the solution is decreasing with time t, right? Similarly, if x is negative, x dot is positive, and the solution is increasing, xt increases with t, right? Now focus on the y coordinate. If x is 0 and you are on the y-axis, if y is positive, then y dot is positive, and therefore y increases as t increases. So the arrow is telling you the direction as t increases, okay? And similarly, when y is negative, y dot is negative, so y is decreasing as t increases, right? And what you can do is, if you take any point which is outside these coordinate axes, you can look at the direction. So let me give you one particular example. Suppose you take any point x comma y in the first quadrant. X dot is negative x. Because x is positive, x dot will be negative. So xt is decreasing, but yt is increasing, right? Which means that the tangent direction is going to be in this direction, right? And this is going to happen for all points in the space. So if x is equal to y, then this slope is 45 degree from the left side. But as if let's say x is more than y, then the left component is more than the y component. And therefore, what you can do is you can actually show that the solution curve will look like this. As if you start with any initial condition here, the solution curve will take this form. As t increases, it goes in this direction. Similarly, here you can fill up the curves. It goes in this direction, it goes in this direction, and it goes in this direction. Right? Okay. So in dynamics, this situation is called a saddle situation. Okay. This is happening at the linear system level. Now, let us go to the nonlinear system. So let me write down the nonlinear system again for you. So nonlinear system for us is x dot is equal to minus x and y dot is equal to x square plus y, right? So now let us draw the same picture. This is x coordinate, x axis, this is y axis. And let us focus just around origin, okay? Now, when is x dot 0? When x is 0, which means on the y-axis, right? Which means that if your initial condition is on the y-axis, which is x equal to 0, then the x coordinate does not move at all, right? So therefore, the picture will be very similar to what we had earlier. If you start on this axis, which is the y-axis or x equal to 0. Now, when is y dot 0? Y dot is 0 when x square plus y is 0, which is this parabola. Right? On this curve, y dot is 0. That means if you start with a point here on this curve, then y coordinate does not move. So what am I saying? If you start here, then what happens is y dot is always 0. So y direction remains constant, x changes, right? And how does x change? X change in the same fashion, right? Because it is negative of the sign of x. So in this direction, this is how the solutions look like. And again, you can fill the remaining region. So remaining curves will look like this. Okay. This is local picture. Okay. So what this theorem tells you is that locally, you can go from this picture to this picture via some h. So let me give you what that h is, which takes you from this picture to this picture. This h looks like this. H of x comma y is equal to x comma x squared by 3 plus y. So exercise, check that h composed with pt xy is equal to e a t h of xy for all xy in. So even though Hartmann-Grogman theorem gives you a local picture, but in this example alone, it is actually a global picture. So this happens for all xy in R2. Now, how will you check this? You can solve this system with initial condition xy or x0, y0, if you're comfortable with that. I have given you explicit h. You can compute this matrix exponential because you know what A is. So this is something that you can check. So the idea is, if you know this local picture, which is easy to get, right? It's just looking at this matrix and figuring out how the trajectories look like, you know that the qualitative behavior is going to be the same, meaning that there will be a curve on which if you start, you're going to approach 0 as time goes to infinity. And there'll be a curve where as time goes to infinity, you will go to infinite. And no other trajectory is going to approach 0. Everything is going to diverge off to infinity. So whatever is happening here will happen here locally. Okay. So this is about this example, but let me also tell you that this hyperbolicity of A, which is the Jacobian matrix, is required. Okay. So let us look at this example. Actually, a series of examples. Consider x dot equal to 0, x dot equal to negative x square, x dot equal to positive x square, and x dot equal to x cube. Okay. Now, again, 0 is an equilibrium point, right? F of x here is 0, f of x is minus x square, f of x is x square, f of x is x cube. All are 0 at 0. And for all these three systems, the linearization is this first system, about 0, right? Now let us see the qualitative behavior of all these systems individually. What happens to the first system? X dot is 0, that means x does not change with time, meaning that if you start with any point on the real line, you stay there. You don't move at all. Let me describe it this way. You don't move at all. What about the second system? Origin is an equilibrium, and if x, now see, it's x square, which means that it does not depend on the sign of x, and it is always negative and x is non-zero. That means it's going in this direction, right? Meaning that if you start with an initial condition here, you go to minus infinity as t goes to infinity. And if you start with an initial condition on the right hand side of 0, as t goes to infinity, you go to 0. You can't cross 0 again because 0 is an equilibrium. Now, what happens in the third system? Again, it happens this way. What about the last system? When x is positive, it is positive. When x is negative, it is negative, right? So in terms of qualitative behavior, these are different systems because here everything is fixed, nothing moves, right? So around 0, if you start with a point, you stay there. But here you don't stay there. Everything either converges to 0 if you are on the right hand side, or it goes off to minus infinity. Here again, it doesn't stay there, right? It either goes to 0 or it goes off to plus infinity. And here everything diverges, right? So the local behavior for all these three systems around 0 is not same as the behavior of this linearized system. Okay. So when eigenvalue has a 0 real part, then you cannot claim anything about the qualitative behavior of the nonlinear system using the linearized system. Okay, so this is a one-dimensional series of examples which give you why hyperbolicity is required. Okay. So now let me give you a formal definition of a dynamical system. So you already know it by now, but let me write it down on paper. So what is a dynamical system? A dynamical system is a triple X, P, and Phi, where X is the state space, P is the parameter space, and P is a map from X, from P cross X to X, describes the evolution of points in the space X as parameter from the space, parameters from the space P changes. Okay, and now you have several examples of this triple already. So rest of the lecture is going to be focused on discrete dynamical systems. Okay, so you may have heard of this area of mathematics which is known as ergodic theory. So let me explain what this subject is in the nutshell. So as is the feature that we have been talking about so far, which is to understand long-term behavior of orbits, right, in a space, you want to have the same question. You want to ask the same question as to what happens to the long-term behavior of solutions. So this area started in the mid-19th century by Boltzmann. During his work in statistical mechanics. And this term ergodic comes from two words, ergon and odosh, so German words, where ergon means work and odosh means fun. Okay. So, and it all started with a hypothesis, which is known as ergodic hypothesis, which says that if you have large systems of interacting particles which are in equilibrium, then the time average along a single trajectory equals the space average. Okay. Now, it may not mean anything to you at this moment, but and we will come to the precise statement in some time. But what turned out that this ergodic hypothesis was false in general. And then mathematicians started to work out conditions under which such a hypothesis, or at least a version of this hypothesis, will be true. And that led to the birth of this entire theory, which is known as ergodic theory, the subject known as ergodic theory within dynamical systems. So, as I said, you want, when you talk about a dynamical system, a discrete dynamical system, you have a state space and you have a rule or a map, right? So there are various categories which are studied here. Okay. The first one is when X is a topological space, generally compact, and T is a continuous map from X to X. Second is when X is a measurable space or measure space, and T is what is known as a measurable map. And third is when X has some differentiable structure and T is, say, a diffeomorphism. Okay. So depending upon where you are, the first, if you are in the setting, which is the first setting, you call it, you fall in the area of topological dynamics. The second one is classified as measurable dynamics, and the third one as differentiable dynamics. So depending upon the properties of the space, you have a map with properties that relate to the structure of the space. So if it is a topological space, you talk about continuous maps or homeomorphisms depending upon the structure of the map. Or if you have a measure space, then you talk about a measurable map. And if you have a differentiable structure, then you have a diffeomorphism on the space. Okay. So that depends on what the problem is. And there are mathematicians within dynamical systems or within ergodic theory who are working in topological dynamics or in measurable dynamics or in differentiable dynamics. Okay. So my examples are going to be mix of especially the first two. Okay, so I'm not going to focus on the last bit. Okay. So let us now look at some examples. And I'm going to start with examples that we already know. So I'm going to now illustrate this deep connection between the doubling map and the shift map on sequences that we talked about yesterday. So let us see, what was doubling map? So doubling map was on 0, 1 with 0 and 1 identified, and X goes to 2X mod 1, right? And then the shift map. Now I'm going to focus on just sigma equal to 0, 1 and X to be sigma to the n, which is sequences on 0, 1, right? So these are called binary sequences because there are only two possibilities. And then you have a shift map, which basically shifts. This point goes to X2, X3, and so on. So it shifts one position to the left. Okay. Okay. So now all of you know that each point X in 0, 1 has a binary expansion. So what is a binary expansion? Meaning that you can write X as X1 by 2 plus X2 by 2 square plus X3 by 2 cube and so on, where Xn belongs to 0, 1. And this shorthand, it can be written as n goes from 1 to infinity, Xn by 2 to the n. Okay. Now, what about binary expansions of points in 0, 1? Is it unique? Now, last time somebody asked me a question about what does doubling map do to point 0 and half, right? And then I told you that there is this collection of what are known as dyadic points. Natural numbers P in N, there are these dyadic points which all go to 0, right? So what happens is these dyadic points do not have a unique binary expansion. In fact, all these points have 2 binary expansions. And other than these points, every other point has a unique binary expansion. So I'm not getting into how one obtains a binary expansion, but this is something that you can study on your own. Okay, and it's an interesting topic to know. So now the question is, why am I talking about binary expansion? Because I want to use this binary expansion to connect doubling map and shift map that I have described just now. So if you look at this binary expansion, let me write this as, in the sense of sequence, let me connect to this point the sequence x1, x2, x3, and so on, right? And this goes in this space, right? So given a point x, you come up with the binary expansion and then you associate a point here. Of course, if you look at these dyadic points, then there are 2 expansions, right? So there are 2 points here. But when you look at those 2 binary expansions, what happens is one of these end with infinitely many ones. So for example, if you look at the point half, half can be written as half plus 0 by 2 square plus 0 by 2 cube and so on, which is same as 1, 0, 0, 0, 0, 0. Or it can also be written as 0 by 2 plus 1 by 2 square plus 1 by 2 cube plus and so on, which is 0, 1, 1, 1, 1, and so on. So half has 2 binary expansions. So what we are going to do for making things unique is we are going to ignore expansions like this. So all these points have 2 expansions and one of the expansions end with ones, and we are going to ignore all of those. Okay. So in turn, when you have the sequence space, you consider all the sequences of 0 and 1 except for those which end with infinitely many ones. And then there is a 1-to-1 correspondence between a point here and a sequence here, because any sequence, any point here has a unique binary expansion which does not end with infinitely many ones, and that relates to a point here. Conversely, if you start with a sequence here, you have a point here. Okay. Now let us connect these 2 maps. Okay. So now let us look at, so consider x equal to x1 by 2 plus x2 by 2 square and so on. And let us apply this map T of x. What does T of x do? It does 2x mod 1. So it will do this mod 1, right? Which becomes x1 plus x2 by 2 plus x3 by 2 square and so on, mod 1. You can prove that this sum is strictly less than 1, in fact, less than or equal to half. Therefore, when you apply mod 1, it's going to act on this part. Now, what do you know about x1? x1 belongs to 0, 1. If it is 0, then mod 1 does nothing. But if it is 1, then mod 1 is going to kill this x1, right? So in any case, this is going to be x2 by 2 plus x3 by 2 square plus so on. But what is the corresponding sequence then? Sequence is x2, x3, x4 and so on. So what did you start off with? You started off with a point having sequence x1, x2, x3 and so on. But when you applied the map T, it has gone to this new sequence, which is x2, x3 and so on. But this is something that you already are aware of. This is just the shift map, right? On sequences. Because on sequence space, if you take any sequence like this and you apply sigma map, you get this image. That means at the level of the space X, at the level of this 0, 1, 2, 0, 1, you have the doubling map. And at the level of sequences, 2 sequences, you have the sigma. And there is this connection, right? Which is via the binary expansion. And this map commutes. This is what we have basically proved here. So, but why is it important? This is an important technique in dynamical systems where instead of looking at the original map, you look at another map which is easier to understand and has this feature that there is a conjugacy or this diagram commutes. This is called the two maps being conjugate or semi-conjugate. Okay, so I'm not going into those technical terms, but then what you do is rather than understanding this T at the level of definition of T, you look at this shift map, which is easy to understand, and then you transport all the properties of this shift map back here to arrive at properties of this T. And remember, the sigma is easy to understand because you know that you're shifting one place to the left, right? So this is the connection that I was talking about yesterday between doubling map and shift. So are there any questions at the moment? So I hope my screen is visible still.
Yeah.
Okay, good. So maybe we can take up questions later. So let me now move on to an important concept in dynamics, which is known as recurrence. So let us understand what recurrence is. So let us go back to this example of rotation map. Okay, when you're rotating by an irrational angle. So yesterday I stated a fact that the orbit of any point on the circle under a rotation by irrational is dense on the circle. Which means that if you look at the orbit, it's going to march everywhere on the circle. Or at least it gets close to sufficiently or arbitrarily close to any point on the circle, right? So that idea is called, that idea leads to something which is known as recurrence, where you say that you keep revisiting the original point again and again. Okay, in what sense? So let me explain this theorem to you, which is actually has nothing to do with any knowledge of dynamical systems a priori. So if you have taken a course in analysis, you should be able to understand this theorem. It's known as Birkhoff recurrence theorem. So it says that let T goes from X to X be a homeomorphism on a compact metric space X, then there exists X in X and a subsequence Ni of natural numbers such that T Nix converges to X as I goes to infinity. Okay. So what is the starting point? Starting point is that you have a compact metric space and you have a homeomorphism on it, meaning it's continuous, it's a bijection, and inverse is also continuous. Then there exists a point in the space and a subsequence of natural numbers such that if you iterate X Ni times as I varies, that goes to X. Now, what are these points? These points are part of the orbit of X, right? What was orbit of X? Orbit of X was these points T and X as N varies from 0 to infinity. You are taking a subsequence from here and you are saying that that subsequence converges to X. What does it mean? It means that if you have the space X and you look at this point little x and you take any neighborhood around this point, then after a cutoff for I, for large enough I, all the T and I X are going to lie in this point. So that means that when you look at the orbit of X, it's going to, so I'm going to draw a continuous orbit, but it's actually a discrete orbit. This X may go, sorry. So this X may go anywhere. It will come back to this one, this ball. It will again go wherever it wants to go. It will again come back to this ball. It can go anywhere, again come back to this ball. So infinitely often it is coming back to any small neighborhood of X that you take. This idea is called recurrence. Okay, so the point keeps on coming back as close as you want to the original point you started off. And all you need is a homeomorphism on a compact metric space X. So if you look at the rotation map on the circle, circle is compact, rotation map is a homeomorphism, therefore this should happen. So for rotation map, there is a recurrence, which means that if you take orbit of any point with irrational rotation, it's going to come back to it. Okay, so this is for irrational rotation. So let me write it down here. So example, irrational rotation of the circle has this property of recurrence. Okay. So now let me introduce to you an application of ergodic theory to proving a very famous result in number theory. Soumya, you have a question?
Yeah. So if you consider instead of irrational rotation, a rational rotation, in that case, it's basically you'll have a subsequence which is a constant sequence, right?
Yes. So, thanks for asking this question. I didn't pay too much attention to that because once you have a fixed point or a periodic point of a map, then this will always be the case, right? So if you have a periodic point X, so let me explain that to you. So what I'm saying is that if there exists X in X such that T Px is X for some P greater than or equal to 1, then T and P X is equal to X for all n greater than or equal to 1. And therefore, if you look at this sequence T and Px as n varies, that is a constant sequence X, right? So
Yeah.
obviously it converges to this. So if you know that your homeomorphism has a fixed point or a periodic point, then always this theorem is satisfied. Right. So
right.
interesting thing happens when you know a priori that there are no fixed points, there are no periodic points. Even in those situations like irrational rotation, right? Nothing comes back to itself. Even in those situations, you know that there is a point which has this recurrence feature. In fact, for irrational rotation, it's very special. For every X, you have a recurrence property. So it's not just, there exists a point, you can prove that for every point this happens. Okay, I hope, Soumya, I have answered your question.
Yeah. Thank you, ma'am.
So this was a very crucial point that if you have periodic points like this, then this theorem doesn't give you anything. Okay. So now, Subhamoy.
Yeah, ma'am, I have a question.
Yes.
In the case of the circle, if we take the irrational rotation or rational, and then any point is recurrence, right?
Any point?
Is a recurrence point.
Yes.
So if they are also and the irrational rotation is a homeomorphism of the circle.
Right.
Now my question is, instead of taking irrational rotation, if we take any homeomorphism on the circle such that any point is a recurrent point, is the dynamics of this homeomorphism same as the irrational rotation on the circle?
So see, homeomorphisms on circle are very close to rotation maps. Okay. There is something called a rotation number that you can associate to any homeomorphism. It basically captures, so what happens for a homeomorphism on a circle? Can it wrap around twice or 1.5 times? No, right? It cannot, because when you take a homeomorphism, it has to be a 1-to-1 mapping.
Right.
Right? So doubling map is not a homeomorphism, right?
Right.
So when you take a homeomorphism of a circle, it has to be something which keeps the circle as you move from, let's say, origin to origin. It does something a kind of a stretching or some kind of deformation of that circle itself. It cannot come back. It cannot wrap around, right? So not every homeomorphism is rotation, but there is a close link between homeomorphisms on circle and rotation maps. Okay, so it will become too technical if I state it there, but towards the end of the lecture, I'm going to give you a reference which precisely talks about this connection. I'll also tell you the chapter number, which you can refer to for this. So homeomorphisms on circle are talked about, are well-studied examples in dynamical systems. They have very precise kind of structure.
Yeah.
Okay. But see, identity map is a homeomorphism, right?
Yeah,
So
yeah.
it's quite possible that nothing happens. But you were
Nothing
talking
happened,
about
yeah.
recurrence, right? When there is recurrence. Right? Even there is recurrence, but in a different way. So you can have, simple rotations. Identity map is also like a rotation. Where nothing happens.
By angle 0.
Yes. So therefore, I mean, there is connection, but again, let me stop here on this answer. Okay.
Okay.
Yeah. Okay. So now let me give you an application of this Birkhoff recurrence theorem, and it's actually called multiple recurrence theorem. So let me state that theorem to you. So this is called generalization of Birkhoff recurrence theorem. So again, X is a compact metric space. Now, instead of one transformation, you have finitely many transformations on X, all continuous. So by the way, in dynamics, we say a transformation. So one is used to transformation in the sense of linear transformation. Here we call it transformation because these are all self maps. So in some way, they transform the space, right? When you apply the map. That's why they are called transformations. They are transformations such that, so suppose they commute. So Ti composed with Tj is same as Tj composed with Ti for all Ij. So they're commuting, they're called commuting, pairwise commuting transformations. Then there exists X in X and a subsequence Ni of natural numbers such that T1 Ni X converges to X, T2 Ni X converges to X, so on up till Tn Ni X converges to X. Now, this is much more stronger than what we earlier said, right? Here we are saying that no matter which T map you take, whether T1, T2, or Tn, there is a fixed X and there is a fixed sequence such that this happens. So there is a common subsequence that has this property. Okay. So these maps Ti's are all distinct, let's say, so they go wherever they want to go. But after the same number of iterations, they keep on coming back to X as close as you want. Okay. Now, and commuting is essential here. So this generalization was used to prove a famous theorem in number theory called So application to number theory, which is called Van der Waals theorem. Okay, so let me state what this theorem is. So it says that let A1 dot dot up till AK be a partition of Z. So by partition, I mean that let us assume that each AI is non-empty, and if you union of all these AIs, that's equal to Z, and they are pairwise disjoint. Okay, that's a partition. Then at least one AI in the partition contains arbitrarily long arithmetic progressions. That is, there exists I belonging to 1 through K such that for all n greater than or equal to 1, there exists A in Z and T in N, for which this set A plus A comma A plus T, A plus 2D, A plus N minus 1D is contained in A. So what is it saying? That there is one of the elements in this partition which contains AP of any length that you wish. So if you decide that n is equal to 100, I can produce an AP or arithmetic progression of length 100 inside AI. Remember, I is fixed. Okay. There is a I such that this happens for all n. If you give me n equal to 10,000, I can give you an AP of length 10,000 in this. Okay. So this result has a long history. Okay. And let me give you a little bit of history here. So let us look at Z as union of A1 and A2, where A1 is the set of prime integers. So plus and minus P, where P is a prime, and A2 is all the composite numbers plus and minus. Okay. So when you look at A2, all the even integers are there, right? Because they are not prime. And if you have all the even integers, then obviously A2 has arbitrarily long APs, right? Now the question that was of interest was whether A1, which is also an infinite set, does it have arbitrarily long APs? And this answer was proved by Ben Green and Terence Tao in 2008, where they proved that A1 contains arbitrarily long APs. And they used ergodic theory to prove this theorem. And this theorem is proved using generalized Birkhoff recurrence theorem, which I just stated. Okay. Again, I'm going to give a reference which has proof of this theorem, which you can understand if you have taken a course in analysis. That's enough. And remember that this result does not arise from van der Waals theorem, right? Because A2 already has this property that is the consequence of van der Waals theorem. So proving that A1 has arbitrary long APs, this theorem is not helpful. But nevertheless, this theorem was proved using techniques from ergodic theory. Okay. And by the way, when I said that it has long history, the investigation into this problem, investigation began in 1770 by Lagrange and Very. So it took a long time to actually prove this result that prime numbers or prime integers have arbitrary long APs. Okay. So since we are on applications, let me give you one more application of ergodic theory, which is in quadratic forms. Okay. So another application of Soumya. Soumya, you have a question?
I just had one question. So in the last theorem, is it like constructive, like the proof?
Yes, it is constructive. So you define certain maps. So you use some results from ergodic theory, which gives you recurrence for free. Okay. So there are some generalized versions of recurrence theorems, which tell you that there have to be, these recurrent points are basically the elements of this AP. Okay, so these points are images of that map. Okay, so in that sense, it is constructive. So, and there are also some statistical results there which says that, almost everywhere something to happen. So some kind of asymptotic results are also there.
Okay,
so,
thank you.
So let me now come to this another application, which is on quadratic form. So let me explain what a quadratic map is. So a quadratic map Q from Rn to R is defined as Qx is equal to X transpose Ax. I'm thinking of X as a column vector for a symmetric matrix, real matrix A. Okay. So an example could be A is, let's say, square root 2, 1, 1, square root 2. And this gives rise to the quadratic form on R2 as quadratic map on R2 as square root 2 x1. Sorry, so let me use x1, x2 here. So Q of x1, x2 as square root 2 x1 square plus twice of x1, x2 plus square root 2 x2 square. So there is this conjecture called Oppenheim conjecture, which states the following. So if Q is a quadratic map, or it's called a quadratic form, in more than 3 variables, which means that n is greater than or equal to 3, such that A is not a multiple of a rational matrix, and A is not definite, by which means that there exist x and y in Rn such that q of x is less than 0 and q of y is greater than 0. So it's neither positive definite nor negative definite. So there are points which have images with opposite signs. Okay. Then if you look at the image of Zn, what is Zn? Zn is just looking at points in Rn having each coordinate as an integer. Okay, so this is called the integer lattice in Rn. If you look at QZn, then QZn is dense in Rn, in R. Okay, so if you just look at the integer points and you apply the map Q, then the image set becomes dense in R. What does it mean? This means that if you take any real number and a small neighborhood around it, there will be an integer tuple in Zn whose image falls in this interval, right? That is called density. So, which means that, so let me, because there are some undergrads, so let me explain this concept. You take any real number in R and any neighborhood here, so there exists so Q of K1 dot dot Kn is in this interval here where Ki belongs to Z. Okay, no matter how small interval you take, there will be some K1 to Kn. And this result was proved by Margulis in 1987. By the way, this conjecture was there since 1953, and it was proved by Margulis in 1987 using techniques from ergodic theory. And I'll tell you what he specifically proved. That first of all, it was known that this result, for this to prove this result, it's enough to look at the case n equal to 3. N equal to 3 describes all the other cases. In n equal to 3 case, what it showed is that how the group SO21 acts on the coset space SL3R mod SL3Z. And he used techniques from ergodic theory to prove this. And this area of dynamics is called homogeneous dynamics. So this is another result where ergodic theory was used, and one of the conditions in this result is straightforward, which is that if this condition that A is not a multiple of rational matrix. Why? Because it is very much like rational. So if you take a matrix which is, let's say, a rational matrix, meaning all the entries are rational numbers, and you apply it on a point which is an integer point, right? So you will see that what is going to happen is, if you apply a rational matrix on an integer matrix, very quickly you will start to see that it will become again an integer vector in Zn. So you will not see that it is going to become dense in Rn. So this exercise all of you can take, that if you have a quadratic form which is, let's say, coming from a rational matrix, then QZn can never be dense in R. That you can see. Okay. So I hope it is making sense. So what I'm saying is, if you take a rational matrix and you multiply with a vector which has all integer entries, then you will see a pattern, because if you apply the map enough number of times, you will become an integer. The point will go to an integer. So therefore, this is kind of something that we have to take, because otherwise there won't be density. So A being not definite is something that is crucial here. Mukta, you have a question?
Yes, madam. Multiple means real multiple, right?
Real.
So matrix can be irrational as well.
Yes. Yes. Any multiple of a rational matrix.
Thank you.
So, how much time? I have about 10 minutes. So let me give you another flavor of recurrence that happens in dynamics. So I was hoping to define ergodicity, but I'm not going to do that because that will take some time. So let me talk about another notion of recurrence. And let us make things more precise in some sense. So this is called Poincare recurrence theorem. Okay, and it requires a concept. So let me first define what is a measure preserving transformation. So those of you who have not taken a course in measure theory, it's okay. All of you would have taken a course in probability theory, right? So think of a probability measure space. So let X be a probability space. So when we talk about a probability space, we have a set X, we have a collection of subsets of X, which is known as a sigma algebra. So if you're not aware of it, just think of some collection of subsets of X, and then a measure mu. So think of mu as some probability measure on this space. What is a probability measure? Mu of X is 1. Okay, so the measure of total space is 1. So let X be a probability space, and let T going from X to X be a map, measurable. So by measurable, I mean that if I take T inverse of any B in the curly B, this collection, and I take inverse, then it again goes to B. So T is known as a measure preserving transformation if measure of the inverse of any set is same as the measure of the original set. Okay. All right. So now you might wonder why we are looking at inverse of T for two reasons. One is that by the definition of measurability of a map, inverse of a set is in B. Okay, so therefore we can talk about measure of that set. Secondly, what is T inverse B? By definition, T inverse B is all those X in X such that T of X belongs to B, right? So this means that you're looking at all the points in the space which go to B if you apply the map once, right? So you're saying that as your map moves, it transports the same amount of information from one place to another as far as the measure goes. Okay. So with this definition, let me state Poincaré recurrence theorem. So theorem states that let X be mu be a probability space and let T going from X to X be a measure preserving transformation and let A belongs to B and A naught be all those points X in A such that there exists Nj increasing sequence of natural numbers such that T and J X converges to belongs to A. So let us understand this collection A naught. You start with any point in any set A in the sigma algebra. You look at all those points in A such that their orbit comes back to A infinitely many times. Okay, so this is another kind of recurrence that given any set in your space, you're looking at those points X in A, which comes back to A again and again, which are coming back to A again and again. Then measure of A naught is same as measure of A. Remember, it's a measure preserving transformation. So what it is saying is that if you are in a probability space and you take a measure preserving transformation, what is a measure preserving transformation? Measure of inverse of any set is same as the original set. If that happens, then for any set A in the sigma algebra, almost every point is recurrent. So in measure theory sense, you are saying that if the measure of A naught, which is a subset of A, is same as measure of A, remember A naught is a subset of A, right? So you are talking about a special kind of subset in which all the points are recurrent. You are saying that measure of the set of all recurrent points is same as the measure of the original set, which means that almost every point in A is recurrent. Keeps on visiting A repeatedly. Okay, so I'm going to stop here. I think I have given you enough flavor of what kind of problems are discussed in ergodic theory. I mean, it was a short time to talk about all the aspects, but my intention was to talk about more and more examples. And this idea of recurrence is the fundamental idea that one sees and wants to understand in dynamics. So I'll stop here. Subhamoy, you have a question?
Yeah, ma'am. I have a question. Is that I don't understand why A naught is a non-empty set.
Okay, so see, recurrence in some sense comes immediately. Okay, so so you can write A naught in a certain way, in the following sense. So let me write down A naught differently. Okay? So the point is, it's telling you that A naught is non-empty. Okay, if provided A has non-zero measure, right?
Yeah.
So it is telling you that yeah. So I should say that if measure of A is positive, then A naught is of course non-empty, comes from the fact that measure of A naught is positive, right? So A naught can also be written in this way, that all those X in A such that for each N, for each capital N greater than or equal to 1, there exists N greater than or equal to N such that T and X belongs to A. Right?
Yeah.
So by this, you can actually write A naught in as a union of sets.
Okay.
Okay, you can write it as union over N of something.
Yeah.
And using some measure theoretic arguments, you can immediately show that the measure is positive, using those monotone convergence theorems. Okay.
Right.
So
Okay.
that's basically the proof.
Okay, ma'am. Thank you.
Okay, so the idea is you write it in as T inverse of the original A in some way, and then you use measure preserving property to prove that it's an increasing sequence or decreasing sequence of sets with certain property, certain measure, and then you have these monotone results, right, in measure theory. So that's the idea of this here.
Okay, thank you, ma'am.
Thank you, ma'am. Let us all thank Professor Agarwal for such an engaging introduction on dynamical systems, motivated with examples. The floor is now open to all for asking questions. If you want to ask any questions, you may raise your hand. Participants on YouTube, you can put your questions in the chat box. We will communicate it to our speaker. Harinder, are there any questions on YouTube?
No.
Anybody wants to ask any question? We can wait for a minute for that. Yes, Kothai, you may unmute yourself and ask your question.
Ma'am, this dynamical system is now an active area of research, right?
Yes.
So if I have to do my research in that, from where do I have to start? Like, what is the basic thing? While starting the research itself, we won't start directly with dynamical systems. Right?
So
What will be the basics?
So see, through these two lectures, I have given you two areas. One is where you work on systems that come out of solutions of ordinary differential equations. So that's the continuous setting. And second is these discrete systems, right? So if you want to start off as in this area, you have to learn. So this area actually overlaps over several areas of mathematics. So you should know topology, you should know measure theory. Okay, you should be good at analysis. The current area of research, if you are aware of, if you have heard of Mariam Mirza Khani, she also used geometrical ideas there. So it overlaps over several areas. So the starting point I would say would be to do those courses well. Okay, learn all those basics well. And then if you want to learn dynamical systems on your own, I will suggest, which I should, so I will suggest a few references to start with, which will give you a flavor of various kinds of dynamical systems possible, ranging from continuous to discrete. Then depending upon who your research guide is, where you end up, you will be working on those class of problems, right? So it's an active area of research where people are working in differential dynamics. There are people working in topological dynamics. It's a small group in India, a very small group of people working in ergodic theory, I would say. But if you get into applied, then there are these engineering departments who work on numerical or applied areas. So I would say on your own, if you want to learn dynamical systems, let me do that. Let me share my screen with you and give you a few references which I intended to give. So I will share my screen again with you. So these are some references. Some of these were already there in the abstract of this two lectures. So the first one is Introduction to Dynamical Systems by Brin and Stuck. It's an elementary book which talks about lots of examples and various aspects of dynamical systems. The second book is more systematic in the sense that it has concepts, it has theorems, it has proofs, it has examples. Okay, so second book is the book I was referring to during the lecture. The second chapter in this book talks about van der Waals theorem and its proof. It has recurrence. It talks about recurrence and a proof for van der Waals theorem using generalized Birkhoff recurrence theory. So this is a very good book if you want to start off learning this subject. Then third book is by Perko, which talks about qualitative study of ordinary differential equations. So what I talked about yesterday and all this Hartmann Grogman theorem and other results. It's also a very elementary book. It's also quite inexpensive. So this is something that if you are interested in the ordinary differential equation side, then you can pick up this book and start learning on your own. It is very appropriate for somebody who has done a course in analysis and linear algebra. Then there is very nice book on differential equations, dynamical systems, and introduction to chaos. If you want to also look at the physical aspects, also the fifth book, which is by Steven Strogas. So these two books, fourth and fifth, will have some applications. So if you are interested in physical applications of dynamical systems, you can look at these two books. And the last book is something that came out of an AIS school that happened in IIT Delhi in 2017. And this is also quite inexpensive. It's by Hindustan Book Agency. And it talks about several dimensions of dynamical systems. So it has a chapter on topological dynamics. It has a chapter on real dynamics, maps on real line, real spaces by Professor Kannan. It has all by Indian mathematicians working in various areas of dynamics. It has about 6 to 7 chapters ranging over various aspects of dynamical systems. So if you are interested in dynamical systems and learning more, I would say that you look at the last book first to see what are the different kinds of directions in which one can go into. Okay. So yes, these are all elementary books in the sense that with very basic. These are meant for undergraduate, senior undergraduate, and early graduate students. So I can
Thank you so much, ma'am.
put them in the chat box. If, can I send a message to everyone?
Yes, ma'am. You can open the chat and use the meeting group chat option.
Okay, fine. So I'll send the list there.
Yeah, it's come.
Any other questions?
Anything on YouTube, Harinder?
No, I don't.
Okay. While we wait for a question, perhaps we can take a group picture. If everybody could turn their cameras on, we could take a group picture. Perhaps we can wait a couple of minutes further. Okay, everybody ready? Soumya sir, Harinder, can you people also take a couple?
Yeah,
Just
sure.
in case.
Yeah, I do.
Okay, thank you. Do we have any more questions from the participants?
Nothing on YouTube.
There's a question on YouTube, Harinder?
No.
Okay. Okay, perhaps we can end it here then, if nobody has any question.
Yeah.
Okay.
Just thank ma'am again.
Yeah. On behalf of Curry Leaf, once again, we would like to thank Professor Agarwal for taking her precious time to deliver this talk. We hope to see you again in our future events of Curry Leaf. We shared a link earlier to get updates about our future events. Kindly join the WhatsApp group for further updates. Thank you very much. Good evening, everyone.
Thank you so much, everyone, the entire Curry Leaf team for your efforts.
Thank you.
Thank you, ma'am.
Yeah, thank you, ma'am. So should we end the live stream?
Yeah, we should.